Hi students, welcome to Optimization Tutorial 5. Today I'm going to discuss a test function which we are using throughout this course, and we are going to find the minimum point for this test function. I'm Dr. Ganguly. Now in this tutorial you will learn about this particular text function in terms of n-dimensional form of this function, and we are going to find the stationary point of this function. Now you have seen this function in its one-dimensional and two-dimensional manifestations. So in one dimension we had the function f of x is x square plus e to the power minus x, and in two dimension we have f of x is x1 square plus 2x2 square plus e to the power minus x1 minus x2. Now I have actually found the minimum point of these functions in tutorial 3, so you can check that out about how to find the minimum point of a function using typical calculus based methods, that is basically taking the gradient and setting that equal to 0. Now you can also take some time to look at optimization lecture 4 for a review of the basics in this course, particularly things such as necessary and sufficient conditions, KKT conditions, convexity, and so on. And of course make it a point to check out the optimization playlist for the full course. Now if we take the functions I showed in the previous slide and we extrapolate it to n dimension, then we get a function of this form here. So now I have f of x is x1 square plus 2x2 square plus 3x3 square plus all the way to I xi square and then all the way to n xn square. So essentially this is one part of the function, and the second part of the function is plus e to the power minus x1 minus x2 minus x3 minus x4 all the way to minus xi and then all the way to minus xn. So this is the general form of the function for which we have seen the one-dimensional and two-dimensional manifestations in the previous slide. Now if you are somebody who likes to think of things in terms of summation signs, then you can write this function in a more compact form. So we can say sigma I is 1 to n I xi square plus e to the power sigma I is 1 to n minus xi. And then if we expand this particular function out, we are going to get the function we have written here. So now the question is to find the stationary points of this function. So let's try to do that. Now, of course, we know that if we want to find the stationary point of a function, we have to take the derivative and set it equal to 0. So now we will take the derivative with respect to some general coordinate or design variable x subscript I. And so that's why I have kept a term involving x subscript I here, because that's going to make our life simpler in terms of figuring out how to differentiate this function. Similarly, there is a negative xi term here. So when we take df by dxi, that simply becomes 2i xi. So we differentiate this term here. So we get the 2i xi because the derivative of xi square is 2xi. And then of course you have a negative sign and the exponential expression, because what happens with differentiating the exponential expression with respect to xi is that you get the expression back, but then you differentiate this particular series here minus x1 minus x2 minus x3 all the way to minus xn with respect to xi, and that gives you a negative 1. So that's why this sign becomes negative here. So now I got this derivative of the function with respect to xi. Now if you are confused, you can actually check this out by differentiating with respect to, for example, x1, x2, x3, and then figuring out how this particular general term comes about. Now for the necessary conditions for a multivariate function, I need to set all these partial derivatives to 0, which is equivalent to setting the gradient vector to 0. So df by dxi is 0, I is 1 to n. These are the n equations I'm going to get out of this particular necessary condition. So let's do that. We set this gradient vector or term of the gradient vector to 0, and so there are going to be n equations of this form. Now if we take a look at this equation, let us try to look at its particular components using I is 1, 2, 3 to n to get the hang of these equations. So first I put I is 1 and so I get this equation here. So it simply becomes 2xi and then this term remains same. Then I put I is 2, I get 4x2 minus this exponential term is 0. I put 3 here, I get 6x3 minus this exponential term is 0 all the way to 2n xn minus e to the power of this x1 minus x2 term is equal to 0. So I essentially now have n equations of this form. And you will of course see there is a certain pattern in these equations. All the terms which have this exponential term, they are all exactly same. So I can look at these n equations and I can write 2x1 is 4x2 is 6x3 is 8x4 is 2ixi is 2nxn. And if you want, of course, you can also obtain these equations by subtracting any two equations here. So let's say I subtract the first from the second. I'm going to get 2x1 equals 4x2. So that's going to give me the first equation. Then let's say I subtract the second from the third. That's going to give me 4x2 equals 6x3. And so I'm going to get all these equations here. Now looking at these equations, I can divide this entire expression by 2 and so I get x1 is 2x2 is 3x3 is 4x4 is ixi is nxn. So this equation in green gives you one of the equations which will certainly help us figure out the solution. So essentially all these design variables are related for this problem and the relationship is given by this set of equations in green. Now let us see if we can extract anything more out of the problem, because this green set of equation, this gives us some idea about the solution, but it doesn't really solve the problem. So what we do is we take this particular solution or set of equations and we put it in the equation which essentially sets the gradient to 0. And let's start with the first equation. So the first equation was for the case I is 1, in which case I had the equation 2x1 minus e to the power minus x1 minus x2 all the way to minus xn is 0. Now at this point you could have taken any of the equations, but the first equation comes out to be the simplest one to take. So once I have taken this, I can rewrite this out. I can actually replace the x2, x3, x4 to xn term in terms of x1 by using this system of equations. So what would happen is that x2 would become x1 by 2, x3 would become x1 by 3, x4 would become x1 by 4. Then we would have the term xn, which would be x1 by n. And that's what I've done here. So the powers of e here, they become in this form. So essentially I have all these in terms of only x1. Then what I do is I take the x1 out here and I get this series 1 plus half plus 1/3 plus 1/4 plus all the way to 1 by n. Now this particular series is actually a series of numbers, and this series of numbers can be represented by, let us say, h subscript n. So this is a sum of all the reciprocals of the natural numbers. So now I have this particular definition, and with this definition I can write this equation here as 2x1 minus e to the power minus hn x1 equal to 0. So this is a compact way of writing it. All I have done is I have replaced this sum here by h subscript n. Now we have this equation in green and we want to solve it. Now of course you could try to solve it numerically, but looking at this equation and from our previous experience in tutorial 3, you know that there may be some way of solving it using the Lambert-W function. So if I could write it in a form a e to the power a, then I could put the Lambert-W function on both sides and then this would essentially help me out. So let's try to do that. So I take this equation in green and I bring the exponential term to the left hand side, so I get this equation here. Now what I do is I multiply the equations, both sides of this equation, by hn, and I divide both sides by 2, so that gives me this equation here. And by doing some of this manipulation, I am able to express the left hand side in a form which is similar to this a e to the power a form which is required by the Lambert-W function. And so at this point I can immediately take the Lambert-W function on both sides of this equation, and what happens is that the left hand side becomes much simpler. Dr. Lambert walks into the room and then it becomes simply Hn x1, and the right hand side becomes W Hn by 2, and so I obtain a closed form solution of x1 as 1 by Hn W Hn by 2. Now this closed form is going to help me depending on the different cases I have. Now let's just write all the solutions out so that you know what we are up to. We had this function in red, which was the test function we started with. Now, like I mentioned in many of the numerical problems we are going to discuss in the later chapters, we are going to use this n-dimensional function and we are going to solve, for example, the steepest descent method, the gradient based methods, and so on, using this function, or at least we are going to use this function to show the working of those methods in example problems. So now we obtained x1 and we of course have this set of solutions which relates x1 to x2 to x3 and so on. So I can immediately then obtain all the different solutions, that is x2 becomes x1 by 2, x3 becomes x1 by 3, x4 becomes x1 by 4, and xn becomes x1 by n. So essentially if we are able to obtain x1, we can immediately obtain all the remaining solutions or the remaining design variables for this particular optimization problem. Now let's check this method out or this solution out for the simple cases which we actually solved in tutorial 3. So the case n is 1 corresponds to the one-dimensional function, that is fx is x square plus e to the power minus x. And in this case, if we consider this x to be simply x1, I can say x1 is 1 by hn w hn by 2. That was the general solution. And I replace n by 1. So I get this form here. Now, of course, you know, since hn was given by this series representation, h1 is simply going to be 1. That's only the first term of this series. So then I can get x1 is w half from this equation here. H1 was 1, so this 1 by 1 becomes 1 here. So only W 1 by 2 remains. So W half is of course the value of the Lambert W function at half, and that comes to 0.35173. Now you can think of the Lambert W function just like we think of the gamma function or the Bessel function, and we can find it from many places. Now one of my favorite places for finding the Lambert W function is the mathematical system known as Wolfram alpha, and here I simply type Lambert W half, and lo and behold it gives me 0.35173, which is the solution here. Of course it gives the solution to a huge number of decimal places, but I'm not a mathematician, so I am satisfied with only 5 decimal places. Now let's check out the case where n is 2. Now n is 2, the function was fx is x1 square plus 2x2 square plus e to the power minus x1 minus x2. And in tutorial 3 we have solved this particular problem. But here in the general solution I take the case of x1 and I know x2 is going to be x1 by 2. And now I calculate h2 using this expression for hn. So you can see h2 is immediately going to be 1 plus half. So we retain only two terms of this series, and that is 3 by 2. So the solution becomes x1 is 1 by h2 w h2 by 2. So I've substituted n is 2 in this general solution for x1, and immediately I put h2 is 3 by 2. So I get here x1 is 2 by 3 w 3 by 4. So remember h2 was 3 by 2. So h2 by 2 is 3 by 4. And so I have 2/3 into the Lambert W function of 3 by 4, and that comes to 0.46915, and then I get 0.31276 as the solution. The solution for x2 becomes x1 by 2, which becomes 0.15638. And do check out tutorial 3 if you have not already done so for the solution without using this particular general statement of the problem. So let us just see how W3 by 4 was obtained. And again, what I did is I went to the Wolfram system and I typed in Lambert-W 3 by 4 and I got 0.46915. I'm satisfied with 5 decimal places, but the system actually gives me a plethora of decimal places here. So you can keep as many decimal places as you like to keep. Now this problem is a very nice problem because it actually lets you get the minimum solution for a multivariate function, and also it introduces the Lambert-W function in this nice way. And this function is generally a well behaved function. In tutorial 4 I have shown that this function can be convex. At least I have shown it for the case involving 2 dimensions. Now I leave it as an exercise for you to show the stationary points here are minimum points, or at least try to prove it for the general sequence. In that case, of course, you have to calculate the Hessian matrix and show that it is positive definite. And there are methods in matrix theory which you can use to do that. So that's left as an exercise for the students. The more difficult problems I will leave to you. So today we discussed the test function which we are going to use throughout this book in many places, and we showed that the stationary point of this function can be obtained as a closed form solution in terms of the Lambert-W function. And so now that we know the stationary point as an exact solution, if we use numerical methods, which we are going to do in the next part of this course, then we can easily check how close we have converged by comparing with this particular stationary point. So do remember to look at lecture 5 and review all the lectures from 1 to 5 before you embark on the next part of this course, which will involve one-dimensional search, and then we are going to get into the direct search methods in optimization, including the gradient based methods, conjugate gradient methods, Newton methods, and so on. So I will see you in my next video, tutorial 6, sometime soon.